I understand how you got that, and I expect some people that you fell into the trap.
Oh,
That's actually not the answer.
okay.
It's simpler than you think. But I'm asking some statistics, starting to see how many people put that answer. No, you're, in terms of the magnitude of the forces, yeah, no, you're absolutely right there. That, it should be that, except recognize the charge of the electron is negative. So there'd be an extra negative in there. Go into the trap as well. All right, why don't we take a look as a group? The reason I do this example is there's two major approaches to dealing with this course, much more than what 251. You play strict adherence to the math, or you think through part of it and don't have to worry about as much math. The most common wrong approach on this is to look at what is the force between these two charges. Now, if you plug into that equation over there, or what was written over here, if you plug into KQ1, Q2 over R squared, the only difference between this and that is that the charge is negative. We have a negative charge there, so we would end up, the force between these two, negative 5.76 times 10 to the negative 29th newtons. The force between this electron and proton, negative 5.76 times 10 to the negative 29th newtons. There's the forces acting on the electron, and then the mistake comes when people just add them. What does the negative mean?
Negative charge.
I would agree that there's a negative charge present, but mathematically, what does the negative charge mean?
Less than 1.
Pardon?
Less than 1.
I think that is not a helpful way to look at it. Vector math-wise, what does the negative mean?
Opposite direction, not the opposite of the negative.
Don't wait. Say it again.
It says move in the opposite direction, like.
Opposite to what? The full formula, so again, the formula with the formality of it, electric force on 2 from 1. This would be R1 hat. If this right here is negative, what does that tell you about the direction of the force?
To the left.
Not necessarily. Or you're half right?
In a standard XY plane, it would be to the left. Is that
But we're not dealing with standard XY plane, we're dealing with R hat. What is the radial unit vector? Still partially up there.
So he said it's going towards the center.
So in this case right here, this is the force that's acting on this electron from this charge right here. So this is the force on the electron from proton, we'll call this 1, proton 1, with respect to that proton. When I'm looking at the force on this electron from this proton, this is my center. Negative means, or sorry, a positive force means it's going away in the r hat direction. Negative means it's going towards. So this is acting to the left, as Joseph had said. What about the force on this electron from that proton?
Right.
You're still going to get a negative here, but now the center is here. And so relative to this, it's in the negative direction or towards it. So when I look at the forces acting on the electron, what is the total force?
0.
Yes. The electron is in equilibrium. Or, said a little bit more clearly, in equilibrium. When dealing with direction I will say throughout this course, when dealing with the direction, it is often convenient to first think about, all right, what's the direction of the air, what's the direction of the force? Because we're dealing with positive and negative charges. It's generally relatively simple. When we get to magnetism, we throw another twist into it. But when we're dealing with just charges, the direction of the force, you can figure out with, is this positive, negative? Okay, they're forces towards each other. Same sign, away from each other. So the electron is being pulled in both directions by the same magnitude of force. Total force is 0. That's the easy approach. In this case, that's the easy approach. We can also do it strict adherence to the math. So the force on the electron would be the force on the electron from proton number 1 plus the force on the electron from proton number 2. This is the strict math adherence technique. Somewhere there's going to be a marker that is bright and clear. So the force on the electron from proton number 1 is negative 5.76. I'm just going to use shorthand. E, negative 29. R, proton number 1 at, plus negative 5.76 E, negative 29. R, proton 2 at. We have two different coordinate systems involved at this point. To come up with a single coordinate system, you know what, it's a one-dimensional problem. I'm just going to make to the right positive. I can get away with that. I could put in I hat if you feel like doing positive I hat that direction, no problem. But in a one-dimensional problem, I can get away with just positive or negative. And so where the electron is located, proton number 1 R hat is to the right. Since R1 hat is going away from the proton, at this point right here, it's going in that direction. There's R1, I'm just going to simplify it, R1 hat. At this point right here, R2 hat is this way. And that is a horrible marker to be using. And so where the electron is, this becomes negative 5.76 E, negative 29, positive. Oh, well, that in and of itself is that way. I guess I can stick in a positive 1. Plus negative 5.76 E, negative 29, and where that is, R2 hat is left. And so we end up with a negative plus a positive 0. There are a number of shortcuts that can take place in this. If you recognize them, you can always do it the long way. Any questions right now?
So you're saying with the vectors, that can be rotated in any direction, and it would be true?
As in, if I have the orientation like that?
Yeah.
Yeah, that'd still be true.
Okay.
All right, let's take a small little break here, and come back. We will fulfill your dream of throwing calculus into this. All right, all's well and good with the plug and chug. Let's do something more complicated. Thin-shelled conducting sphere. Yeah, good enough. In other words, it's hollow inside. And I'm gonna have some test charge up here, the value of it from an academic point of view, it doesn't matter. Make it as small as necessary in order to convince you that what we're doing is legitimate. So I'm just gonna label that as Q1. And then the charge on the sphere, Q2. We'll assume that because it is conducting sphere, because it's conducting, that the charge is spread evenly throughout the whole thing. We're making the assumption that Q1 is small enough that it's not going to disturb that distribution of charge. I need to set up a coordinate system. So I'm going to go ahead and set up a coordinate system so that there's one of the axes goes through charge 1 and the center of my sphere. And just so that I can constantly compare back to my notes to make sure I'm not going too far astray, I'm going to make this the x-axis, the y-axis, and the z-axis. Sorry, I've already changed it, I just looked at it, x, z, and y. Now, which one's x, y, and z really is not particularly significant, other than the fact that there's a lot of little things here, and if something goes off, I need to be able to do a quick comparison between what's on the board and what's in my notes, just to make sure that it's a lot easier to troubleshoot. Or I'll make no careless errors whatsoever, and it doesn't matter which one I do. Now, when I'm looking at the force acting on this charge right here, recognize it as being, in essence, repelled. I didn't give you whether these were positive or negative. If in doubt, assume that they are positive and work through the math. If it turns out to be negative, you don't change anything. All that changes is the fact that whatever value you put in for Q, it's a negative number, and everything still holds true. So you assume that everything's positive. So the force on this is the force from this part of the charge right here, pushing that way. And there's one over here pushing that way, and there's one down here pushing that way. So in essence, we're adding up an infinite number of infinitesimally small forces, which should immediately smack you in the face and say, hey, we're doing calculus. An infinite sum of infinitesimally small things is a calculus thing. So what we're going to do is I'm going to look at a ring of charge right here. What are the chances I can put my hands on the ball? There we go. So imagine that this is my conducting sphere, and I've just basically got a ring around here. I got my test charge out here that is being repelled by all the forces on this ring. Being repelled by all the charges on this ring. And so we'll look at what is that actual force, and then we'll integrate over the whole sphere. Because this ring right here is infinitesimally thin, as I did say, infinitesimally small charges here, this ring has a charge of dq2. Classic differential. Now to figure out what charge is on that, we did make the assumption that the overall charge is spread evenly throughout the surface, and so the surface charge density should be the same. And so surface charge density, I think your textbook uses sigma for that. It's just ultimately charge over area. Or, since we're calculus based, dq over dA. If it's a uniform distribution, it shouldn't matter how big or small I take my piece of area. So if I take an infinitesimally small piece of area, it'll be have an infinitesimally small amount of charge. So dq2 would be sigma times the differential of the area of this infinitesimally thin little ring. So let's define a couple of things here. The distance from my origin, which is at the center of the sphere, so this is origin at center of sphere. Origin at center of sphere. And this would be at the point 0, L, 0. In other words, the distance from here to here, I'm going to make capital L. Try using the same letters as they did before. All right. Remember in the formula we had kq1 q2 over r squared, little r squared. R is the distance from the charge to where the force is the distance between charges, and so this distance here is little r. Not drawn that way, but this ring right here is supposed to be symmetric. It's the point, all the points on the sphere that are a distance little r away. And then the radius of the sphere will make capital R. So the electric force on part one, actually, since we're going to look at this small little segment, it's a differential of the force. It's just kq1 q2 over r squared. So I have my Coulomb's constant, or electrostatic constant, times q1 times dq2. Because we're looking at just the charge coming from this ring divided by r squared. We do need to make an adjustment though. Let's see how well the hand gestures work here. So I got my ring of charge that I'm looking at. I'm trying to figure out the force acting on this ring from this ring of charge acting on some charge out here. We're dealing with vectors here. This is force. So the force from this point right here, if this is pointing, ideally it's pointing straight that way, the force on the point out here is pointing away and down. From down here, it's pointing away and up. So from this side over here, it's pointing that way, and from this side over here, it's pointing that way. It's a uniform distribution of charge, and so any side component is gonna cancel out. Hopefully, the conceptual approach to that works for you. You can work through the math, and you end up with 0. From the way I have it drawn, any horizontal component of the force adds up to 0. That was worded badly. The total sum of the horizontal forces adds up to 0. Any horizontal component of force is canceled out by 1 from the other side. So the horizontal component from here is going to cancel out with the 1 from here. The 1 from here is going to cancel out with the 1 from there, and then all the way around the circle, they will all have a component that cancels out the horizontal forces. The only thing that survives is the vertical force. And so we need to somehow take that into account. Let's set up a classic coordinate system. I hat, J hat, K hat. So only the J hat component is going to survive. So I'm going to create a temporary angle. The angle better not show up in my final answer. But I'm going to label this angle theta. I'm going to label this angle alpha. And so the J component is going to be, so if that's alpha, this is alpha here, it's the adjacent one, cosine alpha J hat. The biggest mistake I see students make, and was Carol's error I make when I'm doing this, is I forget about this, or the students forget about that. So right now, our issue is, I need to find the force here, but at this moment, I have a variable here, I have a variable here, and I have a variable here. I have 3 variables, and so doing integration becomes a lot trickier.